Hello everyone, my name is Haja Faduddin. Today I'm gonna talk about graphic traversal techniques. It has two primary techniques. One is DPS and another one is BFS. The first one is DPS, which means depth first search, and second one is BFS, which means breadth first search. Graph traversal is a fundamental concept in graph theory and computer science. It involves visiting all the vertices of a graph in a particular order, following the edges that connect them. Two commonly used graph traversal techniques are depth first search and breadth first search. DFS explores as far as possible along each branch before backtracking, while BFS visits vertices in increasing order of their distance from the starting vertex. Understanding graph traversal techniques is essential for solving various graph related problems and designing efficient algorithm. Depth first search. Depth first search DFS is a graph traversal algorithm that explores as far as possible along each branch before backtracking. It starts at a given vertex and explores as far as possible along each branch before backtracking to the last unvisited vertex. DFS can be implemented using a stacked data structure or recursively. The algorithm marks each visited vertex to avoid revisiting it and to detect cycles in the graph. DFS is often used for tasks such as finding connected component, detecting cycles, and solving maze or puzzle problem. Here are the some DFS algorithm steps. Choosing a starting vertex and mark it as visited. Push the starting vertex onto a stack. While the stack is not empty, do the following. Pop a vertex from the stack. If the popped vertex is not visited, mark it as visited and process it. Push all the unvisited neighbors of the popped vertex onto the stack. Repeat step 3 until the stack is empty. If there are any unvisited vertices remaining, choose one as a new starting point and repeat the process. Here are some examples of DFS. Consider a graph with vertices A, B, C, D, and E, and edges AB, AC, BD, BE, CE. Let's perform DFS starting from vertex A. We start by marking A as visited and push it onto the stack. We pop A from the stack, process it, and push its unvisited neighbors B and C onto the stack. We pop C, mark it as visited, process it, and push its unvisited neighbor E onto the stack. We pop E, mark it as visited, and process it. Since E has no unvisited neighbors, we move on. We pop B, mark it as visited, process it, and push its unvisited neighbor D onto the stack. We pop D, mark it as visited, and process it. Since D has no unvisited neighbor, the traversal is complete. Now coming to BFS, breadth first search is a graph traversal algorithm that visits vertices in increasing order of their distance from the starting vertex. It starts at a given vertex and explores all its neighbors before moving on to the next level of vertices. BFS uses a queue data structure to keep track of the vertices to be visited. The algorithm marks each visited vertex to avoid revisiting it and to detect cycles in the graph. BFS is often used for tasks such as finding the shortest path between two vertices, testing bipartiteness, and solving level-based puzzles. Here are the some steps for BFS algorithm. Choose a starting vertex and mark it as visited. Enqueue the starting vertex into a queue, which the queue is not empty. Do the following. Dequeue a vertex from the queue. Process the dequeued vertex. Enqueue all the unvisited neighbors of the dequeued vertex and mark them as visited. Repeat step 3 until the queue is empty. If there are any unvisited vertices remaining, choose one as a new starting point and repeat the process. Here are some of the example of BFS. Consider the same graph from the DFS example. Vertices A, B, C, D, and E, and edges A, B, A, C, B, D, B, E, C, A, C, E. Let's perform BFS starting from vertex A. We start by marking A as visited and enqueue it. We dequeue A, process it, and enqueue its unvisited neighbors B and C, marking them as visited. We dequeue B, process it, and enqueue its visited neighbors D and E, marking them as visited. We dequeue C, process it, and find that it has no unvisited neighbors. We dequeue D, process it, and find that it has no unvisited neighbors. We dequeue E, process it, and find that it has no unvisited neighbors. The traversal is complete. Application of graph traversal. Graph traversal techniques have a wide range of application in various domains. In social network, graph traversal can be used to find mutual friends, recommend connections, or analyze the spread of information. In computer network, graph traversal algorithms help in routing, network discovery, and troubleshooting. Graph traversal is used in web crawling and indexing to explore and discover web pages efficiently. In artificial intelligence and robotics, graph traversal is employed for path planning, navigation, and decision making. Other application includes compiler design, model checking, and solving puzzles and games. Time and space complexity. The time and space complexity of DFS and BFS depends on the size of the graph. In the worst case, both DFS and BFS may visit all the vertices and edges of the graph. The time complexity of DFS and BFS is O V plus E, where V is the number of vertices and E is the number of edges. The space complexity of DFS is O. V is the worst case, and it uses a stack to store the vertices. The space complexity of BFS is also O(V) in the worst case, as it uses a queue to store the vertices. However, in practice, the space complexity of BFS may be higher than DFS due to the large number of vertices stored in the queue. Choosing between DFS and BFS. The choice between DFS and BFS depends on the specific problem and the desired output. DFS DFS is preferred when the goal is to explore deep paths or find connected components in a graph. BFS is preferred when the goal is to find the shortest path or the minimum number of edges between two vertices. DFS is often used for backtracking and solving puzzles that require exploring all possible paths. BFS is commonly used for level-based problems such as finding the shortest distance or the minimum number of steps. In some cases, both DFS and BFS can be used to solve the same problem, but one may be more efficient than the other. Advanced topic and variation. Graph traversal techniques from the foundation for many advanced algorithms and variation. Bidirectional search combines forward and backward traversal to find the shortest path between two vertices more efficiently. Iterative depending DFS combines the benefits of DFS and BFS by gradually increasing the depth limit. A search is an informed search algorithm that uses heuristics to guide the traversal towards the goal. Dijkstra's algorithm is a weighted graph traversal algorithm used to find the shortest path in a graph with non-negative edges weight. Other variations include parallel graph traversal, external memory graph traversal, and traversal of directed or weighted graph. Conclusion. Graph traversal techniques such as DFS and BFS are essential for solving various graph-related problems. DFS explores deep paths and is useful for tasks like finding connected components and solving puzzles. BFS visits vertices in increasing order of their distance and is commonly used for finding shortest paths and level-based problems. The choice between DFS and BFS depends on the specific problem and desired output. Graph traversal form the basis for many advanced algorithms and variation, opening up a wide range of possibilities. Further exploration can involve studying advanced graph algorithms such as Dijkstra's algorithm, search, and parallel graph traversal. Thank you.